Right, so welcome back. I think we ended the last session by detailing different acquisition functions and different and how you would fit a Gaussian process, and talked about Hebo and some of the results we got. Now I want to switch gears a bit and be talking about maybe more advanced BO topics, especially those related to tabula rasa BO ones and transfer in Bayesian optimization. So for the other two, I think it would be interesting to talk about them, but maybe in later sessions. For now, I'm going to end the three-part series by talking about this transfer MBO or meta Bayesian optimization. Right, so we're going to focus on that. Right, so far, we have talked about Bayesian optimization. However, we talked about Bayesian optimization as a search problem, which meant that anytime you face a new black box function, right, you would need to start from scratch your Bayesian optimization. So what you would need to do is you would need to rerun BO from scratch, and I use tabula rasa, a word here, to describe the idea that we would run, from scratch BO every time we see a new task. Now, why I use tabula rasa, this is a funny story, but when I was doing my PhD, I was actually focusing on transfer learning for reinforcement learning domains. And back there, the tabula rasa idea was very common, or the usage of the word was very common. We always used to say RL is tabula rasa, and we want to transfer and so forth. So I thought to not forget my PhD and actually carry this idea to BO a little bit. However, let's talk a bit more about our problem definition now and actually try to understand, what has been going on in this field. So instead of dealing, with one black box function at a time, in meta Bayesian optimization, what we are going to assume is that we have a set of source domains, so a set of source black box functions, and that we have collected data from. So what's the data looking like? Well, the data is looking like this x f of x, f of x, hyperparameter tuning, hyperparameter values, and their corresponding validation loss, binding energies on a CDR sequence on one antigen and their binding energies. So we have K of those problems, right? So we have K of those data sets, D1, D2, up to Dk. Now the idea is that we are faced with a target black box function. So it could be a new hyperparameter tuning task, could be a new antigen we didn't see before. And now our goal is to actually use that knowledge somehow in order to transfer such that we can start doing well on this target task with as fast as possible. So in other words, we want to further improve the efficiency of Bayesian optimization by relying on related black box functions or related tasks. This is also not it's a relatively new problem, but it's not like we're the first to suggest it. There's a very nice survey by et al. In 2023, last year, which talked about different methods that are targeting this problem. So many of those problems, they actually being targeted in the different components of Bayesian optimization. So for example, people are trying to design transferable surrogate functions, right? Transferable Gaussian processes, let's say. So they look at different forms of priors, or they look at different forms of kernels that take into account, cross-domain knowledge from all those fields. Others are looking at Bayesian neural networks, right, that are trying to do this. But the latest work is looking at neural processes, which I will introduce and actually focus on in this talk. Apart from surrogate design, there are a lot of people who are actually looking at acquisition design, trying to design multi-task Bayesian optimization acquisitions, or trying to do an ensemble of acquisitions. And there's one direction that is actually doing reinforcement learning-based acquisitions. And that is super cool. I'm also going to talk about that. And there are other things. People look at initialization design, and people look at how can you prune the search space from related tasks. If you're really interested in all those, I think a good starting point could be by a TAL survey, but one of the amazing authors that is contributing tons to this direction is Professor Frank Hutter, which I think you definitely should follow and read more of his work if you're actually interested in things related to these types of problems, as well as auto machine learning and Bayesian optimization in general. So we will be focusing on neural processes, and we will be focusing on RL-based acquisition functions. So we're going to detail what those are next. Okay. So what is a neural process? Let's start with that. A neural process, right, is a model that would like to take the advantage of both worlds. The world of deep learning, which is, very representative, it can actually model very complex functions and has like really good capacity, right, of these deep learning models, but also want to take into account the uncertainty importance from stochastic processes. So neural processes are those types of models that are trying to combine the advantages of deep learning from one side and the advantages of uncertainty estimation from stochastic processes in one model. One of the works that has, kind of popularized this was the work from Ganello et al. In 2018. So the idea here is something like this. You have a set of context data. So you're given some point X and point Y, right? So this is a set of context data. And then you're given a set of target inputs, like X, T, and it's a set of them. Now, your goal in a neural process is to predict the value Y target over all these YTs corresponding to these XTs, right? So you would like to predict the target Y for these input XTs, but you would like to make a distributional prediction. So you would like to predict the distribution of these Y targets conditioned on your context points and also your target inputs that, of course, we don't have the Y value for. So the idea is that we are given context data. From that context data and a set of target inputs, we would like to predict a distribution over the Y values corresponding to those. We parameterize the neural network parameters by this theta, right? And then we're going to train this theta in order to give us good distributional predictions. Now, in the original work by Ganello, they assumed that this output distribution is Gaussian, and that the mean of that Gaussian and the sigma of that Gaussian over the target inputs is actually parameterized by neural network. And the way you would train this type of distribution or this neural process is in a meta way. So what you do is you will get data from the source set. You would randomly split this data into context data and target inputs. And then you would just simply update the theta parameters by the likelihood, the log of Y target conditioned on the context data and the inputs that you strip away from the Y. You update the theta and then you repeat. You sample again. You split the data into a context data and a target data set. Then you just do gradient of the log over and over and over and over again. Right. So what's really happening, right, is that I just get a data set. And after I get this data set, what I am going to do is I'm going to split that data set into context data set in which I know the target values, and into a target data set whereby I don't know the Y target values. Then I will try to maximize the likelihood of predicting my Y target conditioned on my context data and my target inputs. And that's what this gradient is trying to do. Okay, simple enough, right? Now, of course, you use a deep network, to parameterize this distribution. So the mean and the sigma are given by a deep. Okay, all good, all good. Right. However, if we really think about it, the importance of a neural process is that the neural network can model very multimodal complex distributions. When we restricted the neural network distribution to be Gaussian, we kind of lost that power and that capacity of the neural network, right? Because the neural network can give me many multimodal distributions, So why am I gonna just restrict myself to a Gaussian distribution? To resolve that came this awesome work by Müller from Frank Hutter's team that I was talking about. And it's an amazing work. What this work says is that transformers can do Bayesian inference. They parameterized the neural process by a transformer. And from our experience, this has been the SOTA model so far. The idea here is that we're going to take, the context data, so X1 observation, Y1 observation, X2 observation, Y2 observation, X3 observation, Y3 observation, okay? And then when we talk about the target data, which I'm calling here XJ predict, what I'm going to do now, this is a transformer architecture. I'm going to try to make a distributional prediction on the output of this transformer, conditioned on XJ prediction, this input and the observation data that I have seen. In order to represent this distribution, they use a Riemannian approximation, if you will, of a distribution. So it's really a histogram, on the output, where you decide number of bins, right? And now your Q theta is actually a histogram, and you try to fit that histogram with respect to those parameters phi. And I think this idea is also nice because it also relates a lot to distributional RL, for you that know, where the people in distributional RL have actually modeled the distribution of the Q values using a histogram as well. So this is a very close idea, which is super cool. And then you train this transformer in a meta way. So you would get your training data, you would split it in an observation and prediction data set, and then you would maximize your cross entropy loss of this Q of theta with respect to the parameters phi. Now, this model has many advantages compared to other neural processes. First, according to our experience, it gives us state-of-the-art regression results. It can allow us to do multimodal distribution beyond Gaussians, because if you look at this now, the multimodal distribution Q phi here could be a histogram. So it's not just a unimodal Gaussian, it could be whatever complex thing it needs to be to model correctly. And it's really well supported because it uses the transformer architecture, which is one of the most wide neural network architecture. So this is pretty awesome. So now, right, the simplest idea could be that we can think of, right, is that, okay, why don't we go plug and play? So what I mean is, okay, let's go to the standard BO loop and actually replace the Gaussian process by this transformer, right? And then see what happens there. Well, it's not as simple as that. And let's think why it's not as simple as that. What we are really aiming for is we want to design an end-to-end learner for Bayesian optimization. So imagine how cool it would be, right? If you have that model, like some sort of a model, right? Some sort of a neural process, if you will, that will take the input, the history of data you've seen so far, and will take some input in your space X, and it'll give you an acquisition value that you are, interested in. So imagine I could actually build a model, right, that will go from X and the history, and it will tell me what form of acquisition value corresponds to this X, given that history. What would be cool about this is that first, it's simple to implement, much simpler than a two-step Bayesian approach, right? It will be scalable, because if it's end-to-end trainable, I can use all the power of GPUs that I have, which is awesome. And what it really does, it has a feedback that is kind of ignored in standard BO, right? Because now the part of this model, right, that is responsible, for acquisition maximization can feedback the part that's responsible for the model, and the part that's responsible for the model can actually feedback to the acquisition optimizer. So those two steps of BO will not be kind of separate anymore, but they can inform each other, which is like super cool. Because then we can learn what acquisition we would like to use, and at the same time, fix the model based on how the acquisition is doing, but also fix the acquisition based on how the model is doing. So this is a two-step, combining the two steps of BO in one, under one loss, that would make it much more effective. Good. But how would we train this? How would we really train this end-to-end model? Because if you want to train it using a standard neural network, right, you would need supervised data. So you would need, X and history and their corresponding acquisition value. But we don't have those corresponding acquisition values. It's not that simple, right? So we don't have this labeled data set. Where is this labeled data set going to come from? Because if I'm going to, just to train this in a standard fashion, right? Well, yeah, I need labeled data, right? If I want to do like supervised training, maybe you can do supervised training for the model part, right? Because yeah, you have X and Y, but how would you do like the supervised training for the acquisition part? Because we don't know the acquisition values. Okay. So rather than doing that, what we could do is we could actually train this using reinforcement learning. Because reinforcement learning, right, does not need at all labeled data. Reinforcement learning only needs a reward function, which is in our case a black box function evaluation. So what we could do is we could train this whole thing end to end using reinforcement learning without needing any labeled data. And that's what we tried to do. So what we tried to do really is we tried to train this thing end to end using reinforcement learning, right? And the idea here would be to make use of RL in order to train this and not anymore rely on anything that's related on supervised data. So really what we can do now is, given that we don't have the labels, what we can do is we can define a reinforcement learning problem to find the parameters of my end-to-end model. So I can maximize with respect to my neural network parameters theta, expectation average over tasks, because remember, I have D1, D2, D3, up to Dk. So now I'm going to try to find the maximum with respect to the parameters of my model, which are the weights. And I'm going to try to maximize on average over all the training tasks I have, right? Some sort of a reward function as a function of the trajectory that I will sample according to my model. So let's step by step take this, right? For every value X, you can decide which one. So you can try different values X's. Imagine you have this model. You can try different value X's, and then you can get the one with the highest acquisition according to the model. You can take that action in the black box function, and then you can measure a reward of that. We're going to talk about the reward in a second. And then you go back and then you continue this trajectory. So that's how you can collect a trajectory and then you can get a reward. And now you can solve this using a, just any algorithm you like PPO or something like that. But the point is that if we define the right reward function and we are able to solve this problem, then we are able to devise an end-to-end Bayesian optimization solve. which is like super awesome. Because this Bayesian optimization solver in this neural network is combining the two steps together, learning the model and learning the acquisition. Okay. Now, of course, this has been attempted kind of before. And one of the most widely used reward functions is the regret. So the idea is that you will take the Y values you have seen so far. So I'm talking about how I define my reward, yeah? So you will take the Y values you have seen so far, right? And then your reward is just the maximum Y value over the rounds or over the iterations so far, right? So if your new Y value is bigger than the previous one, right, that will be taken into account. If not, it will not necessarily be taken into account. However, solving this problem as is does not work. And there are three main problems here. One is there's something called memorization overfitting, because this is like a standard meta-learning problem. So you can memorize, but you cannot adapt well to new context. There is a learner overfitting, where you actually adapt okay, but you cannot generalize well. And there is uninformative rewards, which is what we will focus on. Because the first two steps can be relatively easily resolved, because here you can do well regularization using a technique like Yin et al. In 2019. Here you can do Gaussian process augmentation, data augmentation, which we also describe in the paper. But the more interesting problem from our perspective is this uninformative rewards. Because if you fix those two steps, but your rewards don't provide any supervision, it would be really hard to tune the parameters of your neural network, especially if it's a transformer. Because think about it, what we try to do here is we're trying to learn a transformer by reinforcement learning. So that's not so simple. So let's understand, this uninformative reward concept in more details. Okay. When is this reward, which is based on regret, actually conveying some information? So we define this reward as the summation over the time, right? Like the length of your trajectory of this small RTK. The T is the time step, K is the index of the task. Where RTK is the max, right? From 1 to the current time step of those Y values, i.e. the black box values we got. Okay. But now we notice, right, that the only informative events of this reward, so the only informative events of this reward will happen if the Y value you see at the current time step is better than the best you have so far. So if we see a new Y value which is higher than the max so far, then that will contribute something to the reward. Otherwise, it will not contribute anything to the reward, because that's what the, kind of the regret, that's how it's defined. So in other words, we define how informative a reward is by the event that the YTK is bigger than the max of the Ys you have seen so far. So therefore, for this reward to be informative and thus contribute to the gradient and thus help supervision and reinforcement learning, this event has to occur. Now we can ask the question, well, during the early stages, what is the average number of such informative events, right? So we can ask the question, okay, well, yeah, okay, we need this event to occur, like this is super important, so we need this event to occur. So then we can ask the question, because if it didn't occur, right, we don't have supervision. So now we can ask the question, well, what's the number of such informative events that can happen? To better understand this, let us actually look into the MDP that we have designed in a bit more details. Specifically, let's look at the distribution of the trajectory p theta of tau k. Remember, right, our tau k, this trajectory is nothing but just xy, xy at different time steps for a test k. So it's x1, y1, kk, x2, y2, kk, x3, y3, kk, and so on. Now, the way our model works, or our distribution works, conditioned on the history, right? You would pick a x to try using the transformer model. That's the policy for us. Given that, you evaluate this in the black box, right? And then you get the y that is corresponding to that value. And in this case, the black box is just the data set. So you go query the data set for this xt value, so to say. So you apply that, and then you will get yt in return. And then you collect the rewards as such. So for x1, y1, you get the r1, and what's the r1 is defined as what we show you here, right? And then we get r2, depending on y2, which is also what we show here, and so on, right? So this is how we get a trajectory. So the trajectory, what we do is we start, we go to the transformer, we start with some history, we go to the transformer, we ask the transformer, okay, what is the xt that I need to pick? Now, how do I find that? By evaluating the acquisition, because that's what my transformer outputs, right? Over, a different set of input x, or I can do gradient in x. That's a different story for now. And then I will pick that xt, which has the highest acquisition value. Then I take that, evaluate it in the data set. The data set responds to me with a y value. I add that to my history in the trajectory, and I evaluate that reward from this equation. And then I repeat this process. So that's how I'm collecting my trajectory, right? So that's how my trajectory is found. Now, so the number of possible ways to make trajectories then of this length, you can actually do some combinatorics. And you can actually find that it's a binomial coefficient, in the trajectory length, where nk total is the total number of trajectories you could actually sample. That's how many ways we could make trajectories. Now, with that, what we can show, I don't want to really go into all those details, right? But with that, what we can show is that the number of ways to order those trajectories such that we get informative events. And remember, informative events are events where the new y is better than the best we've seen so far, like you see here, right? Is given by something called a Stirling number of the first kind. So this is a number that is widely known and widely used in combinatorics. But the idea here is that what I really want to show you is that the process I described, how this trajectory is being formed, the number of ways I could arrange that trajectory to get m informative events is given by this Stirling number, which is a function of the trajectory length and the m, how many informative events you're looking for. But after a long time and a long process of not very difficult calculation, to be honest, you can actually relate this problem I just described, which is the problem of how meta BO and how many informative trajectories you could get. You could relate that to a well-known problem, which is kind of the average number of cycles in a permutation, which was actually a 1962 problem. It's like a very old problem. But using that link, what we could actually show is that the expected number of informative events in my calculation, so the expected number of how many y be better than the old y's I've seen in the way I'm collecting my trajectory, is an order which is logarithmic in the length of the trajectory. So the expected number of informative events is logarithmic in the trajectory length. What does that mean? It means that the times the reward affects or is informative and provides some supervision is logarithmic in the length of the trajectory. So it's pretty sparse. So if you use this reward, which is just this reward of regret that we described before, you can prove that this type of reward will have a logarithmic number of informative events in the length of the trajectory tau on average, meaning that it's very sparse, meaning that it's very hard to get a transformer, an end-to-end transformer to actually work and train well. Okay. So now, what's the idea? So now what we have seen is that the way we are going to create, this MDP, or like maybe POMDP, because we take history into account. And actually, if we want to train it with reinforcement learning, and we want to use a regret loss, like I showed you, this max over y, the only time you will get an informative event is when your new y is higher than the max you've seen so far. But that in turn means, by our formulation, that you will only have logarithmic order of informative events, which means that my reward is very, very sparse. Which means that if I am to train reinforcement learning end-to-end in this way, with this reward, it will probably not work well. Right. Now, this problem, fortunately, is very well known for the reinforcement learning community. The problem of reward sparsity is maybe the most researched question in reinforcement learning. So the question here, can we borrow some ideas from RL people, put it in MetaBO in order to get the end-to-end BO happening? And the answer is yes, and that's what this paper in NeurIPS last year has targeted or has solved. The idea here is that to tackle sparse reward in reinforcement learning, there are many ways, right? Like you could do reward shaping, you could do whatever you would like, right? Like there's so many techniques like experience replays, insight experience replays, maybe even add some prior induction, whatever. However, there's a very nice idea, which was proposed by DeepMind, I think, which is like what we call auxiliary task. We can introduce an auxiliary loss that will induce some effective inductive bias that helps the RL agent to learn. So the idea is that instead of just optimizing this thing, we can add some J auxiliary, which is an auxiliary loss that will provide an effective bias for us. And that effective bias could help us when we do reinforcement learning to start getting better and better updates. Now, in standard RL, those auxiliary losses are not so easy to define, right? But fortunately for us, it's not so hard to define those auxiliary losses because we know what BO needs to do, right? We need one step to be a probabilistic model and one step to be an acquisition predictor, right? So what we could do is we can force parts of the network to become a good neural process, which then its output is passed to another part of the network, which is emulating learning and acquisition function. And then if J auxiliary is differentiable, then we can do this end to end. So what we are going to really do, which I think is pretty awesome, is that we're going to force part of the network to become a probabilistic model. And then the output of this is passing through the second step, which is the acquisition. And then we're going to train it end-to-end using reinforcement learning and this auxiliary loss. In order to define this auxiliary loss, we're going to just rely on the standard amazing work of neural processes, where we're going to take my original data set, I'm going to split it into a context data set, remember, and a prediction data set. And then I'm going to define my auxiliary task as just the likelihood of predicting Y conditioned on X and the observation. And I'm going to have a total loss over all the tasks. So as you see, this part here is a regularizer that is working on part of the network, not the whole network, it's a part of the network that is allowing us to become specified as a probabilistic model. And this part is trying to kind of become a end-to-end BO that predicts an acquisition. So this is the whole idea, right? So the idea is that we will use a neural process, but now we will train this end-to-end with reinforcement learning and an auxiliary loss. And then we did so many tests, right, on this. Now, we call our method neural acquisition process, or NAP for short, because it's a neural process that's also learning and acquisition, right? And then we tested this on many tasks. One of them was this hyperparameter optimization problems. So here we have many source training domains. So we have like support vector machine data, linear regression type of data, XGBoost data. And then we have a target, set of domains, which are unobserved tasks. You train on those, and then you take it, and then you do few-shot testing on those. And in this graph, I show you different methods. So I show you random search, I show you standard Gaussian process with expected improvement acquisition. I show you FSBO, few-shot BO, which was previous state of the art. I show you neural process, but without learning the acquisition function. So you just fix expected improvement acquisition. So in other words, in this part, NPEI, you actually get rid of this part. You don't train this part. You say, okay, this is given to me by an expected improvement function. Then we have Optformer EI, which is Google's MetaBO solver based on Optformer. And then we have ours, which is called NAP. What we can see is that we can do better than the other methods on a variety of tasks. And compared to Optformer, because we really have maybe like a smaller network, we would actually need just 2% of the Optformer time and 60% less memory, which I think is super cool. We then tested this on the antigen problem. So here what we've done is we created a set of source training antigens, which we call d-antigen 1, d-antigen 2, d-antigen K. We train on those, right? And to train on those, we actually collected data using mixed traces. So we mixed random search of the CDR sequence, BO of the CDR, genetic algorithm of the CDR. And then we had a set of unobserved test antigens. We again compared to these different methods. And then what you can actually see, which is the method we see here, is that NAP, which trains end-to-end, is actually capable of outperforming others. And again, we did this with the MIP problem. So we actually, again, splitted the tasks into a training set and a target set. In the training set, we actually, again, combined with the different traces with random search, BO genetic algorithms. And then we transferred, this model to few-shot BO on a new set of unobserved problems. And then again, here you can see that NAP is capable of outperforming others. Now, why don't we see Optformer in these two cases? Because Optformer typically needs the name of the hyperparameter or the name of the variable. And here it's very hard to actually give some sort of a semantic to these variables. But what we can see now is that using end-to-end training, right, we are capable of doing well for the first time of end-to-end Bayesian optimization, completely trained by reinforcement learning and an auxiliary task, combining the step 1 and 2 I described before in a meta-BO scenario. Meta-BO, train on some and test on new ones. We also did that on the EDA problem, the logic synthesis I told you about. We took many circuits as the source circuits, and we took some test circuits, which are unsupervised circuits. Unobserved circuits. And then again, we can see that our method NAP outperforms FSBO, MetaBO, GPEI, and also NPEI, which is kind of NAP, but without training the acquisition. Right. So this was a relatively short and sweet, and with this I would like to end the third part of this lectures. We have presented applications of BO that varied from standard hyperparameter tuning and went to logic synthesis, MIP tuning, and antibody design. We then went into standard BO in the two steps how we would solve the BO method, where we would fit a Gaussian process and then we would maximize an acquisition. And then finally, we talked about a transfer in BO, where we were able to transfer from related black box functions in order to solve a new black box function. Our method was able to do this in an end-to-end fashion, all trained using reinforcement learning. And then we proved that if you just use a standard regret as a reward function, you would actually have a logarithmic number of informative events, meaning that the reward is so sparse. And then we devised the solution by an auxiliary loss, borrowing some ideas from reinforcement learning. And then our methods show that we can outperform others. Amazingly, all this stuff is inside Hebo library, which is all open sourced, including the Hebo, standard BO, meta BO, and this transformer BO, neural acquisition process I described. And also we have other high dimensional BO in there and some reinforcement learning as well. So if you're interested, please have a look. But our library, I believe, is easy to use. It's very flexible and it has many different interfaces. So please make sure to use it if you are interested in BO or meta BO. And if you find it useful, please make sure to star the repo, because that's what will help us to continue open sourcing our work. At the end, I would like to thank you. I hope we learned something from this three level courses of Bayesian optimization. And please do follow me if you found what I am doing is interesting on Twitter or X, sorry, and LinkedIn. And please subscribe to the channel if you think whatever we are doing is actually something useful. So with that, I would like to end the series, and hopefully I will see you with more lectures related to more interesting topics. Thank you so much.